So today I'm going to talk to you about some work that goes back probably, from the time I began working with Constraint Dependency Grammar to 1990 when Murayama presented his original parsing paper on Constraint Dependency Grammar. At the time I was a fresh assistant professor at Purdue, and I wanted to work on speech processing, and my thought was, gee, dependency grammars are great because all of the parsing information is stored at the level of the word. And it has definitely a different way of doing the parsing process that actually may be possibly give you a little bit tighter control. And indeed, that intuition is confirmed in this work, as you will see. Contributors to this work, well, a lot of this work that I'm presenting here is Wen Wang's PhD thesis, where she began it at Purdue and then she went to SRI to actually evaluate the language model in the context of large vocabulary speech recognition systems that we were unable to build in our small lab. And it was extremely, I think, important to actually evaluate the model in that way, and actually very gratifying to see the results. And I really do hope that other people will try their language models in similar ways. And Andreas Stolke has contributed significantly to the work and certainly has been the most enthusiastic supporter that I can think of. Other people that should be thanked for assistance through the course of the work, and I'm sure I've left names off, are here. So I would like to thank these people and begin. Now, many of you, I'm sure, know about statistical language models. Basically, in a speech recognition problem, you want to determine the probability of the words given the acoustic. You want to look at the argmax of the acoustic model in the words, and you factor it in this way, where this is the piece that you get from the acoustic model, and this is the piece that you get from the language model. And the traditional language model is some sort of n-gram probability of the word string that's calculated over some small history. Now, there are a number of language models that exist. The traditional ones are the word-based ones, and of course, it's nice. You can build these with very little work to get a 3 or 4 gram. But people began to realize that to get more bang from the language model, have more predictive capability, you wanted to add additional constraints. Sometimes the issue is not just the fact that you want these constraints, but also the fact that you have sparse data. Class-based language models certainly have been investigated, and there are essentially 2 types, one based on some sort of classes based on some sort of linguistic knowledge. So part of speech tag language models is one example, or you could actually do, you can induce classes based on statistical distributional similarity using like the Brown algorithm. Now, there are also structured language models where, and a lot of this work has really come to the forefront in the past 5 years or so, and context-free grammar approaches are certainly there, as well as the more lexicalized ones. Context-free grammars in and of themselves have not been very good for language models, but lexicalizations of context-free grammar approaches have been. So lexicalized context-free grammars are an interesting choice. Tree adjoining grammars, link grammar, and dependency grammar approaches also exist. And we're going to focus on dependency grammar approaches. Now, as we began the work, Wen and I set 2 goals. We wanted to build both an effective and efficient language model. And by and large, if you're going to get people to use a language model, I think both of these constraints are important. You want to get a language model, I believe, as early in the decoding process. You want to get it back at the beginning of the process, because as you prune, you're actually oftentimes removing avenues that you can never add back. And so getting it into the early stages of processing, I think, is extremely important. So efficiency is important. To do this, we integrate multiple knowledge sources, syntactic constraints that will be dependency-based, lexical features, And these will be things like number agreement, but also things to support WH movement and things like that, to account for the fact that you have differences between subject form pronouns and object form pronouns and so on. And the underlying grammar formalism that we selected is constraint dependency grammar. Now, this is going to be CDG 101 pretty quick. So if you have questions, please do stop and ask, because there's time. Basically, a CDG is a for tuple. It's comprised of lexical categories. These are the sort of like the traditional tags, if you will, nouns and determiners and verbs. There are a set of variables called roles, and these roles actually keep track of the dependencies. So they're like variables that you assign parsing values to. And then there's a set of labels that are related to the grammatical function that a particular word would have when it is when the value is assigned to the variable, as you'll see. And then a set of constraints. Now, traditional constraints in CDG were if-then rules, and there were two types, unary and binary constraints. You could actually have had more, but it would have cost you more to do the processing. Unary constraints take n squared time to apply, and binary constraints take n to the fourth time to essentially propagate. So, and ternary constraints would have taken n to the sixth. So clearly, there is a limit to how far you could go. Now, this would have been for a deterministic parser, and the constraints actually could be applied using traditional constraint propagation approaches. And I thought that was actually quite an interesting aspect of the work. An example of a traditional constraint would be determiners must be governed by nouns. So we're going to use the notion of government. So we have roles, governor, need 1, need 2. The governor role actually keeps track of the dependency where something is pointing to its governor and has a particular function when it points to the governor. So for example, a determiner would point to the noun. The noun would be its head, and so it might have determiner and then the position of the noun that it's pointing to. So here is an example, and we're going to focus here on the word did. This is what did you learn? And you can see that there's a variety of what did you learn. There's 4 positions. What is position 1, did is position 2, and so on. And each word has a lexical category. So in the case of did, it's verb, and a set of features. Now each word has a distinct set of features, one feature per feature category. So for example, did has the subcategorization of base. A base form is expecting an infinitive verb, and that tells you an awful lot about what to expect. Its verb type is past, so it's past form. Its voice is active. It's inverted, so the subject is not where you would expect it to be. It's to the, rather than being to the left, it's to the right, and so on. So you can see all of these things actually tell you a lot about the environment where that word occurs. And it has a gap in it because the object is basically fronted in the WH case, and its mood is WH question. And all past tense verbs agree with everything, and so its agreement feature is all. Now, that's a lot of information, but additionally you have this little packet of information here, which basically keeps track of all of it keeps track of the governor of the word did. Now, because it's a WH word, we have found that it's far better, in the case of a WH word, to have the verb, rather than point back to itself, to point at the WH word. It just allows the constraints to settle down very well, and we found this out by working with deterministic parsers, and indeed it works much better also in the statistical model. Then we have the needs associated with the word. Now, every word is going to have a different set of needs depending on its lexical category. Determiners don't have to keep track of terribly many things, but verbs do. Right? So we have a number of need roles for verbs. Verbs often have subjects, objects, indirect objects, for example. We were able to get by, in the case of verbs, with 3 needs. Sometimes the needs are empty, right? So if you look at what did you learn, need 3 is empty. Need 1 is pointing to 3, the word in position 3, and that's its subject. And need 2 is pointing at learn, and that's the needed base form, infinitive form verb. So we have a position for did, we have a part of speech, we have a set of features, we have a set of role assignments. Now, it's interesting to look at those role assignments in that there's a lot of positional information there, right? You have explicit positional information, but you also have the relative position of the word itself did, the modifiees of each of the role value assignments to the roles, and also the relative positions of 1 versus 3, 3 versus 4, and so on. There's a lot of interesting information there that can actually be exploited to put constraints on what you're expecting to see in terms of the sentence. So, as you can see, a parse is represented at the word level. Everything is at the word level, right? Each word has a packet of information, essentially a data structure, a very simple data structure, and a set of label dependencies. So the thing that's kind of nice about that is the grammar can easily be lexicalized to the word level. And it is interesting to note that CDG has a different bias than CFGs. CFGs actually generalize very well. And once you learn a noun phrase, you've got the noun phrase, unless somehow or another you add in additional word information. So a noun phrase in the subject position is not necessarily going to be distinguished from a noun phrase in the object position. CDG doesn't have that ability to generalize. And so it actually must, unless you do something to avoid this in terms of the way you train the model, must distinguish between populations of subject and object noun phrases. So it is, and in fact, it's mildly context sensitive and actually gives you some interesting attributes because of that. So I'm going to talk about 2 attributes of a grammar. James Allen, in his original natural language processing book.
Let me interrupt you for a minute. Could you just go back 2 slides when you first introduced the CDG? Now that I have the example, I want to make sure I understand this.
This guy.
So go back one.
One more.
Yeah, so lexical categories, okay, I know they are the roles.
So let me.
Where are the features in this description?
Oh well, the features would be F. I left it out.
Okay.
But
So
basically it's a vector.
Okay.
Right.
And did can have, like, there will be multiple realizations of did with different feature vectors.
So the way in which it is implemented is each lexical category essentially creates a set of features.
Okay.
Right, so we essentially create a table in the implementation that says if I'm a verb, I can have these kinds of features because verbs tend to all have the same kinds of features. Now some of them might be omitted in some cases, right? So for example, in terms of agreement, there really is no agreement feature in the infinitive case, but you can easily fill that in with a noun, right? And so by and large, the feature set is a vector that would be associated with the lexical category, right?
Okay. And so in this case, the fact that need 3 is not applicable.
Right.
Doesn't make this a different case of did than some other case. Where
right. So indeed, did is only ever going to have one object, right?
Okay.
It just can't have. But made is going to be different, right? So made can have an indirect object and indirect object. Put. Right.
Give.
Yeah. So, but they all have different kinds of things that they're expecting. And in fact, there would not just be one kind of any particular one, any particular kind of verb. And in fact, as you'll see when we do our class-based language model, verbs really do have the highest ambiguity in terms of the types of classes that you can create.
And is this in the lexicon?
Is this so? In the lexicon?
You have somewhere a lexicon which says that did.
So did
would normally not have need 3.
Well, so some of this is stored in the lexicon, right? And again, the lexicon's not really shown here either, but it's in the lexicon, and some of it's in the constraints.
So the constraint might say, for example, that need 3 of this vector is optional and you can skip it, or it's
So
mandatory and you have to.
perhaps the mistake I'm making, but I do want you to understand that there's a foundation for this that was back in the deterministic world. And we did work with the deterministic grammars for a while. And importantly so, because you understand how grammars settle down most effectively when you play around with the deterministic grammar. We did a lot of playing before we actually built the statistical model so that we had some sense of what features worked well together.
Okay. No, yeah, I'm just trying to figure out whether, for example, at least the way you showed it right now, there is no ambiguity in parsing it.
No, this is an example of a parse. I'm not showing you the parsing process. You wouldn't, and in fact, there's no need for me to show you the parsing process to talk about the statistical model. Later on, I'm going to talk about the statistical parsing process. And you'll get to see sort of a parse then. But it will involve the class, the SuperARV, a class assignment, and then link assignments, basically, and that's it. If you go back to the deterministic parser, there's a whole set of things I'd have to tell you about that, and it really is rather unimportant from the perspective of this talk. Okay. So it really, I mean, to only show you one example, parse it's never going to show you the full potential, but it does give you a flavor for, I mean, the take-home notion of looking at that particular parse is the fact that all of that stuff is stored at the word level, and you can almost imagine packetizing it in some way. And it's by virtue of looking at that packet of information that we actually built the class-based language model. So back to James Allen. How well a grammar is going to work for you depends on two aspects. Generality, you want your grammar to be general enough that it's going to be able to handle the unseen sentences that you haven't given it. So you wouldn't want to just memorize stuff. You wouldn't want to create a regular grammar where all you did was know about the training set, and that's all you would ever allow, right? So generality is extremely important. But the thing is, if you're building a language model, there's another aspect that's important. You don't want to have the most general language models. You don't want the most general grammar. I mean, the most general grammar says everything is okay, right? That's not going to provide you with the kinds of constraints to say, whoops, your acoustic model didn't do the right thing, right? So you want to have specificity as well. And so can you learn about the distributions of subjects, objects, and indirect objects is extremely important. Because those are going to be things that will fall into different positions, and then you can use that information in order to allow your model to say, oh, this is, even though the acoustic model says this path is very good, it's not very good because it's messing up something with respect to the indirect object. CDGs are more specific than CFGs, and we believe that this helps predictivity. Now, there is a trade-off, however, and so if you have this universe of hypothesis. Say you are trying to build a grammar that would work very well, and you want to build the tightest grammar you possibly can to enable you to actually allow a particular hypothesis to exist. Where if it's the correct sentence in terms of the acoustic model, you want to be able to enable it to be accepted based on your grammar model. So by and large, if that is the space of hypotheses, that little yellow dot that you need to allow, then you want the tightest grammar, if you will. But if that's not the case, right, if it really is there, then grammar G1 has missed the boat entirely by virtue of being too specific. And it would basically say that path is not good, and you would totally miss out on the correct sentence hypothesis. So you want something that's sort of just right. And how you do that is very difficult, right? There's really, those two aspects I think are extremely important. So there are three questions that we had to answer. What kinds of information can be effectively included in the CDG? Syntactic, semantic, domain knowledge. In the end, we didn't include semantic information. It just caused the language model to blow up too much. And how can you effectively learn the rules from an annotated corpus? Now, there is no CDG tree bank. right? So we are faced with also having to learn the grammar, the CDG, without a tree bank. And so there'll be some issues that we'll have to address a little bit later on. In the end, we use a lot of lexical features, and we also capture the relative position of the role value and its role values modifiee and the position of the word, and also for pairs. And that is actually the way we could learn the constraints. So rather than determiners are to the left of the noun that it's modifying, we actually can pull out these relations that are actually encapsulated in the parse and create unary and binary constraints directly from the parse. And I'll show you an example of a unary constraint in a minute. We also want to lexicalize the grammar rules, and for that we will, in order to build the probabilistic CDG language model, and for that we will create something called a SuperARV. I will talk about ARVs, then I'll show you an example of a SuperARV, and then how can we effectively build a high-quality probabilistic CDG parser and an effective full parser-based language model. And we'll finish up with that. So back to our example.
What does ARV stand for?
Abstract role value. So it's an abstraction of a role value. So the problem with the role values is the fact that there's a position of the modifiee and position of the word. And that's not abstractable. And in fact, ideally, you wouldn't want to remember specific positional information. But you do want to remember the relative position information. So most of the information that's up there for did can be actually pulled out and used as an example of an allowable constraint. So this abstract role value is a unary constraint, and we're looking only at this assignment here, the governor role VP1. And you have the word did. It's category, but we don't remember the word. The abstract role value has a category of verb. It has a set of feature values, and all of these are fine. They're just constants. And then we have the role ID. The role's name is governor. The label is VP. And then we have a bunch of information about the relative position of the word itself, the position of X, and the position of the modifiee of X. And then we also can store a lot of information about the lexical category of the modifiee and the features of the modifiee and so on. And so all of that information can actually be pulled out, and this vector is essentially a parse rule. If it's there, you can allow that kind of assignment. If it weren't there, then it wouldn't be allowed in terms of the parser, the deterministic parser. So an abstract role value essentially is a finite set of role value assignments that you can actually pull directly from a parse. We just did that. This is an abstract role value. And the only thing that's different between what's there is the fact we've thrown away the word, we've thrown away the 2, we've thrown away the 1, but we remember information that was encoded based on that 1 and 2. The relative position of 1 versus 2, the modifiee versus the position of the word, and the information about the fact that you is a pronoun and has those features. So this is an alternative way of representing unary constraints. And in fact, you can also do binary constraints. So for all possible pairs, you can do the same thing. It's again a vector. And so you can actually represent the original unary constraints and the binary constraints simply by reading off all pairs and all singletons.
Can I ask something?
Yes.
I don't know if you already said, but how do you learn all of the...
You'd have to get it from a tree bank, right? So if I have this is a parse, then I can read the rules off.
Fill up all of these from the tree bank.
Yes, you'd have to have a tree bank, right? Or you'd have to be really smart and be able to come up with all possible rules, which we know is very difficult, right? And certainly at this level. Now, the reason initially Murayama wrote his rules as if I'm a determiner I'm going to modify a noun, right? Those are the kinds of rules that you or I could come up with. Actually, it's very difficult for people to write rules like that. One of the reasons why we went down the road of the ARV and the ARVP was I was the only person in my lab that could write a CDG grammar and have it be effective, right? I had intuitions about how to make that the constraint settle down so it wasn't so ambiguous that it wouldn't just come up with a few parses. Right? You want your grammars to basically settle down and give you single parses when it's reasonable for it to give you single parses, and be ambiguous when it should be ambiguous, right? And the students had a hard time with it. So we went the route of saying, okay, it's going to be far easier to give parses like this, right? And extract the parse rules. And as long as we pull in enough examples, we can actually do a good job of pulling the grammar. Now, it is hard, actually, to do a good job of pulling in a good corpus. And in fact, you'll see, we actually use a lot of material because by and large, you want to pull in as much as you can from web resources and so on. You don't want to have to be creating by hand a large corpus and so on.
Mary, can you then generalize an ARV of this kind using backoff methods?
Yes, and in fact, we do use backoff in the language model.
So
And in fact, the nice thing about constraint dependency grammar is you can relax constraints. And because you can relax constraints, it's so easy to think of the backup, right? So what if I don't want to use any of the feature information? Or what if I think some features are too constraining, right? I can just ignore that information and create something automatically that would be more general. So you can actually create families of grammars with CDG where you can make them more general or more specific. And that's actually very nice. Okay. So this is the ARV. Now the SuperARV is kind of like a join on the ARVs that are associated with a particular word. And again, it's going to have a lot of information associated with it. You'll have a lexical category, you'll have the features, you have the role assignments, you'll have the role ID, the label, you'll have the unary position, the positional constraint between the word and its modifiee. And you'll also have these modifiee constraints where it gives you information about the modifiee. So that's like the lexical category. My modifiee is a noun, and I have a determiner pointing at the noun. And then there's also these positional relations among all of the modifiees, and this is actually very powerful. So not only, if you remember, when I pulled out all that information, I pointed out the fact that there was relative positions between each of the assigned modifiees in the position of the word, and all of those constraints are there and can be expressed very nicely in terms of a vector of information. So here is a SuperARV for did. Now, by and large, if you go back and look at the ARV, it was essentially this top piece, right? You had the verb, you had the features, and you had this, right? What I've added is also each of the need roles and the relative positions of the governor's modifiee, the position of the word itself, the position of the need 3 modifiee, the position of the need 1 modifiee, and the position of the need 2 modifiee. And there's an ordering there. In fact, so the position of X is this word is governed by the same word as the need 3 modifiee. Oh, it's before the need 3 modifiee, excuse me. So the merits of the SuperARVs. So what's nice about this, actually, is that it's a vector, right? We've actually taken this information of the whole word did, and we've actually created this nice vector, and those are enumerable and countable, and they can be associated with words in a lexicon, right? So did can keep track of a set of SuperARVs that have been learned essentially from a marked up, essentially a tree bank, right? And you can actually calculate the probability of having this SuperARV assigned to did very easily by virtue of counting. It provides admissibility constraints on the syntactic and lexical environments that the word can be used. There's features, there's all these expectations about the words that can show up before and after it, and it provides a mechanism for integrating all of this knowledge into one packet that can actually be extracted directly from a CDG parse and stored with words of the lexicon. Now, one might think, oh, the number of SuperARVs may grow very fast. Well, you can always create a situation where SuperARVs grow very fast, and it's not going to actually work very well. One way in which you can do that is add semantic labels in and so on as well. We didn't do that, and if you don't do it right, you can actually create sort of a combinatorial explosion. And so understanding how these vectors blow up or don't blow up is extremely important.
If you could go back quickly to the previous slide, the one with the super, yeah. So is the hope that there will be other words which will share this, like maybe hand or something?
Well, so there, indeed, these SuperARVs are shared by a wide variety of words. So did is going to have some things that are very much in common. It shares a lot of properties with modals, right? Like will and could and so on. Distributionally, the frequency of this may be different than the modals, right? Modals don't have other forms of do, other forms like do does. So do can actually be a regular verb. It doesn't always have to, it doesn't always expect a verb as its object, right? It can expect noun phrases, for example, and so on. So these packets are stored, and indeed, if you go back and begin to say, okay, we've got, if we create these tree banks, and indeed we created tree banks, and I'm going to tell you about how they were created, but I want to show you this initially because indeed, if you look at these corpora where we actually have created SuperARV models, the number of distinct SuperARVs does not grow terribly fast. So initially, we created a tree bank for resource management by hand. So we began our work with resource management, and there were 328 unique SuperARVs for that corpus. Then basically we scaled up the Wall Street Journal Penn Tree Bank because everybody had been working on the Penn Tree Bank, and so it was appropriate. So we simply created a CFG to CDG converter, and then used that in order to enumerate the SuperARVs. There were 538. We thought that was pretty cool. That's 1 million words. If you go to the CSR task, a lot more training. There isn't a tree bank, so you have to get your trees in a more flawed way. You basically have to use statistical parsers that were trained on essentially the Penn Tree Bank to provide parses for this and then convert those over into CDG SuperARVs. And that had 37 million words, and we only picked up a couple hundred more. Now, when we do this, we actually are very careful to make sure that we add things effectively. So we are looking for distributional characteristics of objects and so on, because none of the Penn Tree Bank stuff is marked up for things like subcategorization. So there is some tricks that we use in order to pull out those lexical features because they aren't really there in terms of the Penn Tree Bank. Move up to Hub 4, 300 million, 1,612, and then to Hub 5 switchboard, which is 300 plus million, 622. Now, it is interesting because this really sort of highlights, I think, what many people know about switchboard, and that is really how despite the fact that there's lots of words, it's pretty narrow. You know, people are chit-chatting, and so the variety of lexical forms is pretty limited there, which I think is really kind of cool.
Question, could you maybe put a line for the future for what the vocabulary of these things is? Because I suppose that's...
I think that's actually a good idea.
So I know that Wall Street Journal is probably, the Penn Tree Bank is maybe 10K.
10K, yeah, and for CSR it's 20K. And for Hub 4, I'm sure it's more than 20K.
Probably 65.
Yeah. And I'm not sure for Hub 5.
I think that's the thing, the Hub 5 vocabulary is not as big, even though.
Right, it is much more narrow. But the thing is, that you're not getting like all these new kinds of verbs or anything. So to generate the CDG parses, we basically convert existing corpora annotated based with other grammar formalisms, essentially context-free grammars, into the CDG annotations.
Sorry, let me ask, one more question on the previous slide. So is it the case that your real CDG, the growth in the number of SuperARVs doesn't come from the open class words? If you keep adding proper nouns, they're not going to contribute anything new.
Proper nouns don't add anything.
So is that why it's not growing? What's the?
So verbs grow the fastest.
Right.
Conjunctions are pretty high as well.
Okay.
Determiners don't. There's maybe 3 or 4 different classes that you learn,
Okay.
and it's done. Adjectives are, some adjectives don't add very many, and then others, when you have them as predicate adjectives, do have complements. And so essentially, I think the thing that's most predictive is the fact that there are complements associated with specific things. Yeah.
So resource management, the sentences came from an artificial grammar.
It did come from an artificial grammar.
Do you see any differences when you extract them from that versus?
We didn't use the artificial grammar. We used the
text,
sentences.
But you say you didn't see any sort of like subtle influence from it having been generated in that way?
No. It was a nice place to begin. We didn't think doing the full Pentry Bank would be doable in our time. But we did think it was important. And indeed, we built a deterministic grammar for resource management before we ever did the SuperARV experiment. But it was in terms of working with that particular small corpus that so many of the insights were gained in terms of being able to have things work well with the large corpora. So I do think that is an interesting message. You can actually learn an awful lot about grammar formalisms by working on smaller grammars initially and then scaling up based on the insights. And certainly it worked here. So the CFG to CDG transformer is essentially a rule-based system, right? So I suppose this is where rule-based comes together with statistical models, because we certainly don't have a CDG statistical model until we have CDG parses. We use the typical headword percolation stuff that Fred's talked about. I don't want to say who came up with it because I don't remember who you had said it was.
Ezra Black.
It was Black. It has been attributed to others as well, but we use this and we basically can identify the linkages between the governor and its head, between a word and its governor. And then we add need roles to represent the subcategorization constraints. So I put subcategorization in. We actually don't put that in as a feature. We actually allow the roles to learn about subcategorization. And then we derive lexical categories and features using rules. Word identity, we use anything we can come up with. So we use conlex and a variety of other corpora that actually did tell you about subcategorizations. We looked for common types of patterns when we saw parses for particular verbs, and we tried to learn about all the possible types of orderings that you could have in terms of the verbs. So we used everything we could possibly get. So it's not beautiful, and it certainly is errorful, but what we generate is essentially a set of parses. And for the most part, we can tell you that when it came to looking at the training set, we did hand verify that, at least on 3 or 4 sections, that the parses that were generated were correct. And we can't guarantee that all of them are correct, because it would have taken an awful long time to do that. So we start off with this. This is the Pentry Bank parse, and we end up with this, right? These packets of information. So by and large, you have essentially a set of words, features, lexical categories, and role value assignments.
What does count mean here in?
It's a count noun.
No, in the.
So it's a count noun. So count nouns typically expect, so it's expecting a count noun as opposed to mass noun, for example.
So,
So-
under 2, administrations is a count noun, but under 5, the behavior is that it expects a count noun.
Right, so those are very useful things, right? So
And what does the 3S mean there?
it's expecting something that's third person
Pardon me?
singular.
Third person singular.
Right, so you would want to distinguish between third person. So actually, I think Fred actually brings up a very interesting point here. Notice that these assignments are very explicit to the parse. And the actually does have a situation where it expects plural form. Right.
It expects what?
You can have the dogs, for
Yes.
example, and that's okay. So the actually is going to have situations where it expects singulars and cases where it expects plurals. Right, and so there's some ambiguity there. It can be used in different ways. Doesn't have both, right? So you can have a dog, but you can't have a dogs. Or if you do have it, if you happen to see examples where it exists in the tree bank, you'll pull out the SuperARV, but it'll have such a low probability that it's probably not going to make that much difference. But basically, there's a lot of these handshaking kinds of features that are in there. And they were in there for a good reason, because when you have those kinds of things, you have the fact that this thing is count and this thing's expecting a count. Those kinds of things settle down very nicely in terms of constraint dependency grammar. So very, very good question. So we're going to talk about two language models. We'll spend most of the time on the almost parsing language model, but I will go through the full parsing model as well. And doing a full parsing model matters. Unfortunately, the full parser models cannot be applied so early and cannot be applied in the decoding step, and so they can only be applied later. So just quickly, if you take a look here, we have an example of essentially a sentence where we actually also have associated with the sentence the SuperARV. So the big box at the bottom is sort of the SuperARV, and then you have a set of linkages, right? Where this is the governor link of this, and so screen only has a governor link, and it's expecting a determiner, and so on. So in a way, this sort of captures the SuperARV. The only thing it doesn't show is the relative positions, the relative positions between the different need role modifiees. But you can see, actually, in this particular case, that you're awfully close to a parse there, right? All we have to do to have a full parse is to simply say what's going on with the need to for clear, what's going on with the governor role for the, and the governor role for the is expecting a noun to its right. Now, in this particular case, it's so easy to finish up the parse. With longer sentences, it's going to be a little bit more cumbersome to do that. But in this particular case, it's expecting a determiner to the right, and so you can see that you could actually easily satisfy all those constraints, set the pointers, and be done. The almost parsing language model is essentially a class-based model that uses the SuperARVs. Right, so there are tags. So if you go back and pull out what you know about part-of-speech tagging language models, we have essentially, instead of using now, we're using these vectors that we've pulled out. And those are the tags. And we use a joint model, and we factor it in this way. So we have the tags given the prior words and the prior tags, and the words given the prior words and the tags. And after applying this on a word sequence, we would have an almost parse. You can actually do tagging to get the almost parse as well. And only a limited amount of work is needed to get the full parse. Now, what you need to do here in order to build the model is you need to decide which lower order n-grams to use in the interpolation or back off, whatever you're going to use. And you need to decide on a smoothing algorithm. Now, for smoothing, we end up using, we compared a lot of different methods, and we end up using the modified, interpolated modified username. Not surprising. For the n-grams, you want to be able to go back off to a more fine-grained history. And for this, we actually used mutual information in order to come up with these interpolation orders. There is a reason why we end here and here. Going back to the 0 gram doesn't work real well. And also going back to the word here doesn't work very well. It adds noise. And so there is only so far you want to back off. So we back off to the word given its tag, and we back off only to the tag. And of course, ultimately you want to have the probability of the word given its history. And for this, you use a standard formula. And you would do a similar kind of thing with parser-based language models over parse prefixes. So initially, we did perplexity results. We obtained perplexity results on the Penn tree bank. And we were able to compare at the time with some work by Kalba, Charniak, and Rourke, because they all evaluated on the same set and created their language models in exactly the same way. And we were very encouraged in that the SuperARV language model ended up with a very nice low perplexity. It is interesting to also note that we also looked at the correlation. One of the things you should note is the SuperARV does not interpolate with the trigram, right? Now, you might ask, well, why would that be? Well, we have the joint model with the words, and it actually is capturing very nicely the information that is there in terms of the word. If you do a joint model for part of speech tagging, actually it correlates very well with. So if you look at the probability given your trigram model for test sentence and probability of given the joint model, you end up with a very high correlation. Interesting thing is if you have a high correlation, it also tends to be predictive of the fact that you can't interpolate the trigram. Whereas if you look at the conditional SuperARV, so we also used a conditional model. And for that, it doesn't correlate as highly. We also lose a lot in terms of perplexity. And Ciprian's model has a slightly lower correlation, but it is interesting.
It's a correlation between what and what?
The probability on a sentence assigned by the SuperARV language model versus the trigram language model. It is interesting that would show some patterns like that. Now, Charniak's model correlates 0.69, which is a lower correlation, and the model, it's a full parser model. These are all full parser models. Actually does interpolate effectively with the trigram. They all essentially are using the same trigram. Brian's trigram is different, I don't know why. But you can see the perplexity of the word-based trigram right there. Now, on the Wall Street Journal CSR task, so this is the second one, I don't remember how, 37 million words. We compare the trigram language model, a type part of speech language model, the SuperARV language model, with a variety of models. And you can see the SuperARV language model has these were all done with the lattices that Ciprian provided. And so everybody evaluated on that in this particular case. And the lattice accuracy that you can get is essentially 3.41 word error rate. And you can see this is doing fairly well. We actually retrained Ciprian's model and improved it a little bit by running more iterations of EM. But you can see that the SuperARV language model is better than that, but more poorly than Zhu and Kalba. Now, that is actually, I think, pretty good given the fact that it's not a full parsing language model, and it does fairly well here against the original Kalba model. Now, what I'm going to report here is the results that we reported at ICAST 2004. And this was the full CTS evaluation. Now, what you should realize about this is you can apply the full
CTS stands for what?
conversational telephone speech,
Uh-huh.
right? So this is the DARPA ears task. So the CTS task last year, conducted by NIST, the NIST evaluation. So we use the SRI Eval 2003 Spring system for the speech recognizer, and we trained the language model on extensive data. So we had switchboard 1 call home, switchboard 2 phase 2, and so on. And we also added additional material that was pulled from the web by Mari Ostendorf. Now, it is interesting because that extra material really made a difference from the perspective of applying a SuperARV language model to the ultimate lattice that was provided by the SRI system. So adding the additional information that was brought in from the web was very effective for training the language model. We generated parses using a combination of Charniak's and Collins parsers, and we used a CFG to CDG transformer to generate the CDG annotations. So just like we did before, we're doing the same thing here. And we evaluated on the 2002 eval test set. Now, the SRI system is an almost parallel decoding of speech data using acoustic models on 2 front ends. It uses HLDA normalized MFCC caps for coefficients and PLP features normalized using LDA and MLLT diagonalization. The 2 subsystems are then combined using an MBEST rover, and I'll show you a diagram. And we train a number of language models. So the language model that you're applying at various stages might start off as a bigram at the earliest stages. So at the earliest stages, when we apply the SuperARV language model, it's going to be like, well, I'll talk, but it will be a bigram-based model. And as you move along, you can go to trigram. At the end, it's a 4gram, right? So we apply higher order language models as we go along. We looked at we compared the perplexity of the 4-gram language model with a 4-gram language model that was interpolated with a 400 class language model that was essentially induced. So it was induced from statistics associated with the training data. And we compared the perplexity to the SuperARV 4-gram language model and the SuperARV 4-gram language model interpolated with that 400 class language model. The 400 class language model doesn't add anything, which I think is interesting. But we do have a significant perplexity reduction. The language model training, as I said, is all of this stuff, right? And the source-specific language models are essentially interpolated and merged. And the baseline language model uses context-dependent interpolation weights. Now this is the SRI system. And you can see, in the end, you're doing an MBEST rover over this piece. Now, initially, we applied the SuperARV language model here to each of these lattices, and then we do the MBEST combination of or we do the rover combination of the 3. And in that particular case, we do okay. We have a 0.7 reduction in word error rate. But if we go back and we do something where we apply it at all levels, it does even better, as you'll see. Now, there are 2 challenges here. SuperARV language model is associated with the words, right? And so the SRI system has multi-word tokens because of pronunciation models at the early stages. And so we actually had to do some fiddling around in order to get things to work with a lot of. And indeed, efficiency was so important that we actually end up using an ARPA backup. So we are not using, we end up pulling out probabilities for n-grams and do some pruning up front. It's informed based on the language model, but it is not using the full power of the language model while we do these investigations. The time is so important because of the constraints on the DARPA ear systems. They have to be under 10 times real time, you can't actually apply even the SuperARV language model as it was. I mean, it's pretty fast. It's much faster than a full parser language model because you certainly don't have the parse stack that you have to keep track of, but it's still a lot slower than applying an ARPA backup language model. So we basically conditioned the multi-word bigram and trigram language models given the SuperARV language model, and we transformed the class-based language model into the ARPA backup format. So evaluation, as I said, was the RTO2 CTS evaluation set, and we create SuperARV conditioned bigram, trigram, and 4-gram language models. These are all in ARPA backup, and the data was split into a tuning set, with the remaining 72 speakers being used for our bias test set. So we were working with some piece for tuning and some piece for evaluation. The word error rate is compared using the baseline, which was essentially a bigram at the early stages, trigram as you move along, and a 4-gram at the end. And it was the 4-gram interpolated with that class-based language model, because that was the best we could do with the word-based model. As you can see, at the first stage, just simply using the bigram conditioned SuperARV ARPA backoff model, you get a 1.1% word error rate reduction at this stage. And as you move along, you actually gain. You lose a little bit here, but overall, your word error rates are dropping. So this is the this is the absolute reduction of the word error rate for the traditional language model compared to the SuperARV ARPA backup. Yeah.
Are these cumulative, or is this for a...
No, the overall total is a 1.7%.
Overall total for applying the SuperARV at all of the boxes?
So the difference is at each level, right? So at this point, yeah, this is cumulative up to this point, right? So it's 1.5% absolute reduction compared to what you would get in terms of the word error rate from applying the traditional language model versus the SuperARV. This was very interesting because we weren't really sure. I mean, many people say that you're not really sure until you go through all the stages whether or not something is going to work all the way along. It might be that something that you do here would essentially get rid of any gains that you had in the early stages of processing by virtue of applying the SuperARV model, and it didn't end up being so. And I think that was the thing that got people very interested in the model, was the fact. Now, deep down, I would expect a language model is pretty decorrelated from the acoustic model, and so it wouldn't surprise me that this would be also true of any other language model, right? It wouldn't surprise me at all. So I don't think that this is a finding per se for SuperARV language models, except for the fact that we could easily take the model, apply it efficiently, and get it to work very well over all the stages. Using the complete RTO2 set, the baseline language model word error rates versus the word error rates for the SuperARV model. If you look at the bigram recognition, you get 0.7%. Look at the 4-gram recognition, 1.3%. The final combined system using Rover, it's 1.6%. So this is different, but this is the full test set.
And the difference is that in the previous results, you were reporting only on the part that was not used for the weight combination. Yeah. And in this
is the full. Yeah. So adding linguistic knowledge, you can create a compact model, which is really very interesting. The constraints are very powerful. And in fact, you could create, for the modifiee constraints, we're only keeping track of the lexical category. When we do the full parser model, we actually keep track of more. So you could actually build a more powerful model than the one that we have, and then use even other ways of factorizing the model in order to address the sparse data problem. So I do believe that this is only the beginning for this model. I think there's a lot more that you could do to effectively build a family of language models that would be useful. And it helps to apply it as early as possible and to continue processing it and to actually scale up as you go along. And it shows, the specificity of CDG shows some merits. It is really nice because, and you'll see with the parser language model, that more data really does help. If we actually limit ourselves to a smaller amount of data, we can hurt the language model substantially. But data is pretty cheap, and if you can get the parses and you can apply the automatic methods to convert them over to the CDG parses, it's fairly easy and straightforward to get the statistics you need to build the language model, so it's not a big deal. How to get to full parsing? Well, all that remains is the links, as soon as you've done this, the role value assignment. Now, we actually investigated two types. We had a loosely integrated parser, and this is the one we worked with first. Because by and large, it's easy to do the tagging and then do the linking up afterward. But by and large, we all know from the CFG work that a tightly coupled tag assignment with the parse tree is far better. And so we also look at a tightly integrated parser. And this stuff was done very quickly at the end of the thesis. Now, to give you a sense of how the parsing works, here's our example again. You can assign the SuperARVs, and then you begin from left to right, where you start with the word clear. And you go through all the left branching links first. Well, 3 of the links are completely determined. They're just simply pointing at the word itself, because it doesn't need anything for those roles. So clear only has one need. It's an infinitive, so it doesn't need a subject. It doesn't have, it can't take a subject. And it only has a need 2. It needs an object. And it needs an object that's a noun, but that's in the future, right? And so you don't have to do anything. You hit the word, then you move on. You hit the word the. Again, you only have one right branching link, so you move on. Now we're going to work from the nearest word we're going to work on the left branching, and then we'll link up the right branching links that remain to be linked from the prior words. We needed a determiner, and there it is. And then you do the right branching, the links that would branch into this word, and so you've got the noun. Now notice there's a synergy between a determiner needing the word, between the noun needing the word the, needing the determiner, and the being governed by the determiner, and that synergy is actually going to be capitalized on in the model. And then you have, finally, the verb, and there's your full parse. You have to fill in the need. Again, you've got that circular link, which is, again, this is very powerful, a very powerful constraint. Now, the symmetric dependencies are very powerful. They were very powerful when it came to the deterministic parser, and indeed, they're pretty easy to model using a synergistic random variable that allows you to basically say, if I have this link into this word, then I must have a link back to the word that it came from.
You're really simplifying quite a lot, because after all, clear could be replaced by something like push, in which case it could be a noun as well.
Oh, sure. But all those SuperARVs are there. They've all been learned, right? So of course, there's this lexicon, right, where you've learned all of this stuff from the corpora, right? And you've got counts. You've got the probabilities. It's a probabilistic.
No. But I mean, you were saying that
I'm just talking,
that these links just, you know,
well,
they are very simple, and we know what they are, but it's in this particular.
Right. Well, once you do the SuperARV assignment, so this is the loose model, right? As soon as you do the SuperARV, you could be wrong, but you're going to do the best you can, right? Now, in reality, when you do this, of course, you have a parse stack, right? And so you're going to keep lots of parses alive until you get the one that's the best. And by and large, that's the way statistical parser models work. So, I mean, I'm not talking about that. I'm just trying to give the flavor of how this particular, how easy it is to obtain a parse once you do the SuperARV assignment. Yeah.
Does this, when you run this parse, does this use whatever was the one best SuperARV for each word? Or
So we actually run it with nbest initially in a loose way, right? So you do the nbest, and then you can actually do the link ups. And we also do a tight integration of the tag assignments with the links. And that of course blows up much more. It takes a lot more time to apply the tightly integrated one. But it's far.
Meaning all links need to be satisfied.
No, tightly integrated means you do the tag assignment at the same time that you're working on assigning the links, right? So I basically am going to not do, in the best case, I assign all the tags first. In the tightly integrated one, I assign any possible tag. I have a stack, right? And then I'll work with the best one. And I'll start trying to link things in. Then I'll move on to this, right? And so as I add things in, you've got essentially combinatorial explosion, if you will, right? In that this could be combined with lots and lots of incarnations of this and so on, right? You want to keep as many of them alive as possible, but of course you have to set pruning thresholds because inevitably the problem would get way too big. This is a standard issue for all statistical parsers.
Sure. I guess what I'm asking is if it's not tightly integrated, if you run the recognizer with the almost parsing SuperARVs first,
right,
and then if you go back and try to parse,
if I did one best, it wouldn't work very well. I don't think.
Yeah. So you would wind up with the wrong SuperARVs for some
in
words.
Many cases you
that's
could,
what
right?
For the first pass.
So
and
the accuracy,
right.
the tagging accuracy. If I look at Wall Street Journal, so we actually evaluated this, it's about 92%. Right, so it's not anywhere close. I mean, it's not the 98% you get for part-of-speech tags, right? So you do want to look at a larger search space. So having a lattice of possibilities is extremely important, and that's what the tightly coupled version gives you. Is it allows you to explore more assignments at the same time that you're going through and satisfying links. Now, what's nice about the fact that as soon as you move on to the tightly integrated one is the link assignments do actually help you to do a better job of assigning SuperARVs and vice versa. Again, there's a synergy between doing those two operations, which you would expect. I mean, it's the same thing actually with the CFG statistical parsers. Is that if you tightly integrate the tag assignment, and so I guess originally Michael Collins' parser had a separate stage of doing the tagging, and then he also investigated in tight coupling. Eugene always had the tightly coupled tag assignment with the parse. With doing the parse trees.
The splitter temple linked grammar, on the surface it looks very much like this one. Maybe it was Lafferty, I don't know who they had.
Okay, the link grammar, right.
Yeah. So that one had a...
So the difference between CDG and link grammars is link grammars do not keep track of the need roles. They don't. So actually, why keep track of need roles here? Well, it has a lot to do with valency and keeping track of things that are really required, right? You have to keep track of the requirements of a word, and they have to be distinguished. So adjuncts versus complements is an extremely interesting comparison. Nouns can take adjectival modifications, but they don't really need them, right? Whereas if a verb doesn't have its complements, there's something that's missing, and by and large, that might downgrade your belief in that word being the verb that was provided by your acoustic model.
No,
and so keeping track.
They also keep track of it by essentially instantiating multiple versions of clear or whatever it is in the lexicon. But
they don't distinguish between links that are required versus links that are optional.
No, they distinguish them by making two entries, one with each, and so you could analyze.
Oh, but see, having one with each still doesn't tell you whether it's required or optional.
No, so I don't.
If you
because the required one would be there in each instantiation, and the option would then be there in one and not in the other, and so you could use either one.
So we have compared a lot with link grammar. Link grammars did not work very well. In fact, they were never effective as language. But there's a lot of data that that's missing.
What I'm saying is the parsing procedure to do with citing.
Actually, the parsing procedure here is very similar to Jason Eisner's dependency grammar model, except for the fact that we simply use need roles and we did not have those. The need roles are representing information about required aspects of the word. You take that information away, all of a sudden you don't keep track of need roles and you only keep track of governor links, right, which is essentially a link grammar. But the model does far worse. And so actually you can create a family of grammars where you say, okay, all I'm going to worry about is the governor rules, right? That's the traditional dependency grammar. It doesn't work well. Even if you keep all the features, it doesn't work well, right? So the whole packet of information there is actually providing you with a lot of synergistic information that allows the whole thing to work well. I worked a lot with just working with the governor rule. I was working with deterministic parsers, and I knew immediately this is going to be overgeneral. I'm never going to get it to settle down. The need rules are extremely important, and they were there in Murayama's original incarnation of CDG. He did not have features. He added features. So we have synergistic, and we also allow crossing dependencies. Crossing dependencies occur when you have WH movement, because remember we have the verb point to the WH word, and in the case where you have a prepositional phrase, like in what country did you buy that, right? You'd point at what, and under those circumstances you'd have crossing links in terms of the dependencies. And you can actually learn about what crossing dependencies, when a crossing dependency is allowed versus not allowed. We also use distance in our model, and 94% of the dependencies don't cross a verb. They cross verbs when there's WH questions, but in Wall Street Journal Tree Bank, there's not very many WH questions. And punctuation can help. Certainly if you're evaluating the text corpus, you want to use that information as well. So we add modify lexical constraints selectively also. And so you can actually use the traditional SuperARV model that we used for language modeling, where we wanted to keep things sort of on the light side, or you can actually add the full modifiee constraints, so you know all the lexical category information. That blows up pretty much, and certainly we knew that based on the traditional grammar, is that there's such a space of things that you have to learn that you end up creating something that's far too specific, right? So you want to selectively add modifiee constraints. We did this in a rule-based way that I don't have time to go into here. But to sort of give you a feeling for why it's so, when does the number of a noun matter? Well, it matters with respect to the determiner that might be modifying it. It also matters with respect to the verb, right, when it's the verb subject. But if it's the object of a preposition, usually the number doesn't matter at all. And so actually using that information selectively when it matters is extremely important. So you don't want to have to learn about all the possible numbers that would be associated with the object of a preposition in order to actually know about nouns that would be objects of prepositions. Yeah.
I guess this was what I was talking about when I asked about backoff. Is there a way that you could automatically select which of the lexical features then are necessary for particular
So we developed a way of doing this when we were inducing grammars from Harper in terms of the SuperARV, in terms of the ARV and ARVP representation. So we used what we did there in terms of this. So there was actually a way in which we went through and did it in a semi-automatic way with information from, we presented information in an interesting way to me to do the markup, basically. But it took me 3 hours to do the markup, and then we got the enriched features. There's no way I can go through all of that. Now, for the full parser language model, of course, we're working with parse prefixes. You're working from left to right. And so you also, in terms of the statistical language model, you want to calculate the probability that we're given prior words as being informed by the parse prefixes. We use the SCDG, or a statistical CDG language model, the full one, to rescore lattices, and we compare them to several others. Again, this table is very similar to what I presented before with the SuperARV. The SuperARV model that we present here is essentially the same SuperARV model that we had talked about before. This is the SuperARV language model. And then these are the incarnations of the parsing language models. And the basic model has essentially nothing, right? It's the traditional SuperARV. It's working with 50 best 50 best in terms of the SuperARV tag assignment. And if we begin to model crossing dependencies, we gain a little bit. So WH movement matters here. we add a distance model. It helps a lot. We enrich our features for the modifiee constraints. We even do better. So in the loose model, you can see that all of the things that we added matter.
Mary, what's the last line?
That's the oracle accuracy of the lattice.
Oh, that's the oracle. Okay.
So
And
you,
what does
you can get about
What
68%.
does SAC stand?
This is the same lattices provided by Cyprian.
No, SAC is the
Sentence
number of
accuracy.
sentences which are fully.
Right, so if I is the correct sentence in the lattice or not, right? And if I pull out the best, and then if I pull out the best path to minimize word error rate, it will have a word error rate of 3.41. That's just the
The
oracle
oracle in
accuracy.
the lattice is 3.41.
Word error rate.
But if you
And
make
in terms of getting the sentence completely right, it only happens 68.
So if you do 100 minus
I
68.
see, I see, I see, I see, I
that's a
see, I see, I see, I see.
Okay.
Okay.
So now moving from this, we also did experiments where we increased the mbest, and every time we increased the mbest, we did better. But so we went up to like 200 or 300 best, and then we just bit the bullet and went to the type SCDG model. And you can see this improves things substantially. If you look at Cyprian's original model, he was getting 13% word error rate on the lattices. If we retrain it, we run more iterations of EM, we do a little better. And actually, it is slightly better than Zhu and Kelba. Not statistically better, not statistically significantly better, but it does do better. Now, the thing I should tell you, though, is this is trained on far less data. Apparently, the model could only be trained on some portion of the CSR data. We have no problem training on, I mean, our model is pretty economic, so we can train on as much data as we can get our hands on. And so indeed, we could probably
It's
have...
not the training that takes us, it's not the time that we worry about, it's the enormity of the storage
Oh, sure.
that is being used.
But see, we don't, our storage
yeah,
doesn't blow up
okay,
either.
right.
I mean, it's a pretty economical model in terms of size. And as long as you set sane pruning thresholds, actually we do pretty well. So this again is an initial result. We could certainly, I think, improve upon that. We certainly haven't done we haven't added all the possible information that we could to the SuperARV, and we haven't explored different ways of factoring the model and so on. So in the end, I think the thing that should be learned is that tight integration of these knowledge sources is very powerful. We have lexical information, we have modifiee constraints, we have a variety of things that can actually aid in word prediction. Constraint dependency grammar is wonderful in that it provides a framework where you can put a lot of that into a package of information and relax constraints. And so you have a reasonable path for backoff. And it's interesting in that it has a different inductive bias compared to CFGs. And this fact is actually, if we actually train our model on the data that the Zhu and Kelba was trained on, actually we do slightly worse than that model, right? And we certainly don't get the result that we had. So more data matters significantly here. I don't know how much the data matters to the PCFG models because people have not evaluated them. For future directions, we are interested in moving on to spontaneous speech, and in fact, we've done some preliminary experiments where we can add actually SuperARVs to model disfluencies, so to keep track of disfluencies. And actually, we on the switchboard corpus, we actually, by virtue of doing that modeling with the SuperARV language model, reduce perplexity. And it's a significant reduction in complexity. The real problem is how do you get marked up disfluencies in order to train a language model, and that's something that we're wrapping our mind around right now. And we also are interested in applying it to other languages. One obvious possibility would be Czech or Chinese because we have nice resources. Not a lot of data. I'd really ideally like to have a lot more data, but there are some fairly reasonable parsers that have been developed, like Colin's parser works fairly well with Czech, and Eugene's does as well. So we have resources to get what we need, and so I think it would be very interesting to try it on Czech. And we also would like to apply the model to other tasks other than speech. It'd be very interesting to see how well it will work. Whether this notion of tight integration and harsher constraints works well in other tasks. I would think it would. Questions? Yeah.
So at this point, you're basically taking the entire feature vector for a word and use it as one single class, right? Would it make sense to further split it up into a couple of different subclasses to have more data sharing across words?
So the thing that's very interesting is because you have the ability to create things that are more general, right, by virtue of ignoring information, you could create short SuperARVs. And in fact, for smoothing, you often will do that, is essentially you'll smooth based on information on SuperARVs that really haven't been a part of the space that you've been working on. Right, but factoring it in a different way, I think, is extremely interesting, and it's not something that we have done yet. The model, I do think, would benefit from interesting factorizations. So I agree with you. I think that there are other alternatives. The thing is that you get so much. I think the tricky thing is you get so much from the synergy, and so pulling the wrong thing out can really, I think, be catastrophic. A lot was learned along the process of those years of working with the constraints initially, and then working with induced grammars, and what it would take in order to train those induced grammars so that they would perform reasonably in terms of not having too much ambiguity and not generalizing well. Right? Not generalizing well really tends to be more of the problem with CDG, right? And so smoothing is certainly a very nice way of doing that. And it is interesting that doing the tightest model you possibly can, I think, and then backing off to more general models is really the way to go, I think. We did a number of experiments in terms of relaxing constraints, both in terms of the parser and in terms of the language models. And we actually could create things that were essentially similar to other dependency-based approaches. And so there was the Prague dependency tree bank, the PDT, the Prague dependency parser that was done in the Hopkins workshop here, used very few constraints. And you can see if you back off to that, the model doesn't do very well. If you add all the stuff back in, it does very well. You can back off to something that just takes into account governor constraints without the needs. And that does far worse than the one that has all the need rules. So you can actually do a number of experiments that sort of show you how important the different knowledge sources are. And you can actually pull two things out at the same time, right? So you can take some of the features away and see which things matter. And indeed, some things matter far more to the model than others. The need rules are really important. And we did that actually in an EMNLP paper, the original EMNLP paper where we presented the SuperARV language model back in 2002. Other questions? Yeah.
About the conversion from the pen tree bank to your CDG format, what does it take? So if you wanted to do it in Chinese and you had the Chinese tree bank.
Well, the problem with working with another language is you really have to understand, and I think this was certainly true when you guys were working with Czech, is you've got all those features, and you really want to find which features in Czech are really going to be predictive for words, right? So I don't include every feature I possibly can in that packet. I include the ones that are very helpful in terms of dealing with the syntactic, the overall syntactic coherency of the parse, right? So I have number, I keep track of whether there's an inversion, because all of those things sort of work together. There's a synergy between inversion and WH and so on. If you go back to linguistics, you can see that certain things just can't co-occur with other things in terms of the feature space, right? And so how you pick the features is extremely important. And what makes me nervous about working with Czech is I'm not really sure I have the intuitions for Czech about what those are. With Chinese, there's far fewer features, right? And there's also a lot more free order in terms of the words. So I think there's different challenges in terms of working on Czech versus Chinese. In fact, Wen is uncomfortable with the idea of working with Chinese because she thinks that there's going to be less for us to take advantage of in terms of the feature space. And since I don't speak Chinese, I don't have that intuition. I'm looking at the Czech. I think Czech would be more interesting.
So what you're saying is that, but you didn't, for example, take the English pen tree bank and basically extract pretty much everything you could so that you would have very long packets of weak packets and then do some data analysis to figure out what features.
It was a rule-based method. We basically attempted to take the CFG parses and produce an accurate CDG parse.
No, I'm just wondering, you said that there are many features in that packet and you kept...
The features were selected a long time ago.
Right. So
based on grammar induction experiments, right? So the features that mattered in terms of the constraints settling down so that you didn't have blatant ambiguity when there should be no ambiguity, or too specific a grammar such that it would rule everything out, right? You can add lots and lots of features that would essentially memorize the sentence space that you have trained on. There's an art to picking just the right constraints, right? Most of the constraints that were included would be the constraints that tree adjoining grammars would include if they were going to, right? Some of the stuff is captured in the CFG tree bank, but a lot of it's not there. And so, for example, subcategorization is not captured there. But you can actually get an awful lot from marked up corpora that people have. So you've got conlinks, for example, which is very, very useful from New York, NYU. And there's a medline corpus that actually tells you about subcategorizations. And so on. So you actually have to do something in order to obtain the subcategorizations because it's not there in the trees. The number information is typically represented, or you can find the number by virtue of looking things up on online dictionaries. When that's there, you use the online dictionary because you want the information to be as accurate as possible. But the real tricky one was subcategorization. And for that, we did do a lot of interesting work.
Okay, thank you very much.